In the last class, we introduced the Mersenne twistor random number generator. This is a random number generator that is based on bit manipulation and a recursive relation involving bit manipulation. That's different from the linear congruential random number generator, which was based on an arithmetic equation, based on a recursive arithmetic relationship. So the Mersenne twistor random number generator has improved properties of randomness in its random number sequences compared to that a linear congruential random number generator, which has poorer properties of randomness for sequences of random numbers. In today's class, we're going to begin, and this will continue over the next few classes, using this random number generator, using it to generate sequences of random numbers for a class of methods or class of problems that we call Monte Carlo simulations or Monte Carlo methods. So these are methods for simulating or modeling various problems. They're used in physics, but they're used in other basic sciences, and they're used beyond basic sciences, for example, in economics or in business. Monte Carlo simulations are very common in physics. We're going to apply them to modeling radioactive decay as one example in today's class. We'll apply them to Brownian motion as another example in the next class. We'll also apply them to such problems as the gas law for a volume of gas and ferromagnetism for a volume of ferromagnetic material. So today's application will all be based on the random number generator in the NumPy random number package. Specifically, it's the random number generator RANF that generates a floating point number from 0 to 1, a uniform distribution of floating point numbers from 0 to 1. And so we're going to be just calling this random number generator in this particular class and in the subsequent classes on different Monte Carlo methods for different physics problems. Before simulating radioactive decay, before modeling radioactive decay, I wanted just to give you some sort of history, some sort of importance of radioactive decay in the development of physics, especially nuclear and particle physics. So the discovery of radioactive decay goes back more than a century. And the discovery of radioactive decay was the discovery of radiation from naturally occurring minerals that contain radioactive substances like atoms like uranium and thorium. And that discovery was really the birth of nuclear physics, in a sense, the birth of particle physics. And it was awarded a Nobel Prize, the 1903 Nobel Prize. When you think of uranium, when you think of thorium, think of these atoms as being kind of survivors from the birth of the Earth out of matter, out of the material that was created in stars. So the constituents of the Earth, the atoms and molecules of the Earth, came ultimately from stars and from the explosion of stars. And uranium and thorium are unstable radioactive atoms that came from stars and explosions of stars, but they sufficiently long-lived radioactive atoms that they still survive today. So our Earth is about 5 billion years old, and the uranium, thorium isotopes have long enough lifetimes long enough half-lives that they are survivors from the birth of the Earth. Actually, the idea, the understanding that radioactivity is the transformation of one atom of one type to another atom of a different type, that was a breakthrough in understanding that took several years after the discovery of radioactivity. It was sort of the realization that there is a modern alchemy. You can change one atomic species to another atomic species. It was about 30 years after the discovery of natural radioactivity that artificial radioactivity was produced in the lab, was generated in the lab. And so that was another big achievement in the history of radioactivity, that through nuclear reactions, through nuclear experiments in the laboratory, one could artificially produce new radioactive nuclei that don't occur naturally, that aren't occurring naturally on Earth. That also received the Nobel Prize. The 1935 Nobel Prize was for the discovery, the production of artificial reactivity. Whether we're thinking about the decay of a natural radioactive substance or an artificially produced radioactive substance, those decays, those spontaneous decays, are described by what we call a decay law, radioactive decay law. That decay law is sort of the classic example of what we now take for granted, but what at the time was a very bothersome, troublesome issue, and that's the indeterministic nature of the laws of physics at the size scales of atoms and molecules and nuclei. So in quantum mechanics, in quantum physics, we understand that things are probabilistic. You can't calculate, for example, the time of the decay of a uranium atom or a thorium atom. You can only calculate the probability of decay of a uranium atom or a thorium atom. And so radioactivity is the classic example of the probabilistic nature of the quantum world, the world of atoms, molecules, and nuclei. So I wanted to introduce the decay law on this overhead, on this slide. Imagine you've got a sample of radioactive nuclei, and members of that sample are decaying as a function of time. So let's call uppercase N the number of radioactive nuclei, and let's call Dn the change in the number of radioactive nuclei in some time interval we'll call dt. So that's the process of radioactive decay. The relationship between the number of decays, the change in the number of radioactive nuclei, and the total number of surviving nuclei is this little equation here. This is the differential form of the radioactive decay law. So on the right-hand side, we've got N, the number of radioactive nuclei. We've got dt, the time interval we're observing them for. And over here on the left-hand side, we've got the number of decays. In addition, in that relationship, there's this quantity lambda. It's what we call the decay constant. It's a characteristic of the particular radioactive species, whether it's uranium or thorium or something else. And its value determines whether that radioactive species decays quickly or decays slowly. It's the decay rate. It's measured in inverse seconds or inverse days or inverse years. If it's a big number, then that's a radioactive material that decays quickly. If it's a small number, it's a radioactive material that decays slowly. That equation upstairs in this slide is the differential form of the decay law. The equation downstairs on this slide is the integral form of the decay law. So if you take the differential form of the decay law, you separate the variables. You put the n's and the dn's on the left-hand side, the delta t, the dt on the right-hand side. And then you integrate this equation. And then you take exponentials of the left-hand side and the right-hand side. You get downstairs here the integral version of the decay law. This integral version of decay law says that the number of radioactive nuclei that you have surviving at time t is equal to the number of radioactive nuclei you started with at time 0, multiplied by this exponential factor, where in the exponent it's a negative exponent, and it involves the product of the decay rate and the time that you've been observing the nuclei for. So again, if lambda, the decay rate, is a large number, your radioactive nuclei are going to decay away rapidly, and this will be a rapidly falling exponential decay curve. If lambda, your decay rate, is small, you've got slowly decaying radioactive nuclei, then this exponential decay curve will be a slowly falling exponential decay curve. Now, often we write the decay law in terms of the decay constant, but you'll also see often we write it in terms of an equivalent quantity, the lifetime of the radioactive nuclei. So the lifetime tau of the radioactive nuclei is the inverse of the decay rate of the radioactive nuclei. The decay rate was measured in inverse seconds or inverse days. The lifetime is measured in the units of seconds or days. And so this is a second way we'll often characterize the radioactivity of this particular species or that particular species. Now, in that differential or integral form of the decay laws, we had the number of radioactive nuclei and the change in the number of radioactive nuclei. And often we think of those as continuous variables, that n and dn are continuous variables. But actually, of course, n and dn have to be integers. You have an integer number of atoms or molecules. You have an integer number of decays of the atoms. If you imagined recording the number of decays of a radioactive sample in a certain period of time, let's call that recorded number of decays. Let's call that lowercase n, and let's call that interval of time. Let's call that delta t. If you imagine doing that, and you imagine doing that experiment, repeating that experiment many, many times, what you observe is that the number of decays in that time interval fluctuate. There are statistical fluctuations in the number of decays. And that's again because of the indeterministic nature, the probabilistic nature of the laws of quantum mechanics, the laws of quantum physics. The distribution of the statistical fluctuations is given by Poisson statistics, and it's given by this equation here. So in this equation here, m is the average number of radioactive decays in the time period delta t. It's the mean number of radioactive decays in that time period delta t. Imagine you've done the experiment many times and you calculated the mean number of decays. So that's m. N is the number of decays in a particular measurement. So it's the number of decays that you observed in the first measurement. It's the number of decays you observed in the second measurement, the number of decays you observed in the third measurement, as you went about this process of repeating the experiment many times and calculating an average. P of n is the probability of observing n decays, giving that the mean is m decays. So it tells you the probability of n decays for a mean value of m decays. And you can see that over here on the right-hand side, it's just an equation that involves n and m, the observed number and the mean number. I've plotted this probability distribution over here on the top right. So on the horizontal axis is the observed number of decays in a particular measurement. And on the vertical axis is the probability of getting that number of decays. And I plotted it for 3 values of the mean. So the orange points here are for a value of the mean that is a mean of 1. After making the measurement many times, you found that on average, you got 1 decay in the time interval delta t. The light blue points offer a mean value, an average value of 10. If you did the measurement many times and calculated the mean number of decays, you would get 10. And so the orange points show you the probability distribution for different outcomes for a mean of 1. The light blue points show the probability distribution for an outcome, a mean value of 10. If you look at the probability distribution for a mean value of decays of 1, you discover that there's substantial chance, more than 35% of getting 0 decays. There's substantial chance of getting 1 decay, more than 35%. And then there's falling chances for getting 2 decays, 3 decays, 4 decays, but they're not 0. And so that's the Poisson distribution for m equals 1. For m equals 10, that's the light blue point, you just see that the most probable outcome is 10 decays. But the number of times you would get 9 decays or 8 decays or even 11 decays or 12 decays is just a little bit less than the probability of getting 10 decays. And so that's what the distribution for m equals 10 looks like. If the average number of decays is a large number, so maybe if it's 100 or 1,000, that Poisson distribution that describes the statistical outcomes of the measurements changes into a normal distribution or a Gaussian distribution for the outcome of the measurements. This Poisson equation that describes the Poisson statistics changes into this normal distribution or Gaussian distribution for the statistical distribution. And I plotted this equation over here on the bottom right-hand side. So on this plot, I've got the number of decays along the horizontal axis again, and I got the probability of getting that number of decays on the vertical axis again. So the same axes. And then I'm plotting the distribution of those decays for a mean of about 5 through a mean of 10, 15, 20 to a mean of 30. And what you're seeing here, as we walk from a mean of 5 to a mean of 30, is really the evolution from the Poisson distribution, which is important for describing the probability distribution when you have small values for the mean, to the normal Gaussian distribution, which is a good approximation when your mean value, your average value, is a large number of decays. The Gaussian distribution looks like a bell-shaped curve that is symmetric on its left and right. And if you look at a mean of 30, this bell-shaped curve is centered at 30, and it looks symmetric to the left and right at 30. And so for an average mean of 30 decays in your time interval, the normal or the Gaussian distribution is a really rather good approximation. If you look at 5 decays, if you look at the distribution for 5 decays, you see that it is centered on about 5, actually not exactly 5. And also it's asymmetric. There's a longer tail on the right-hand side than there is on the left-hand side. This is not accurately described by the normal or the Gaussian distribution. This curve here corresponds to the sort of asymmetric about the mean Poisson distribution. And so this plot shows you the evolution of the statistical fluctuations from a Poisson distribution where you have low statistics to a Gaussian distribution where you have high statistics. One last topic I want to mention is radioactive decay chains. So often you just don't have the simplest case of a radioactive atom decaying to a stable atom. Often you have a radioactive atom decaying to another radioactive atom, which decays to another radioactive atom, and so on and so forth. That's called a radioactive decay chain. So the decay of uranium is a famous example of a radioactive decay chain. The decay of thorium is another famous example of a radioactive decay chain. And those decay chains and other decay chains are shown on this plot. So let's take the example of uranium. Upstairs here on the top left is uranium, a particular isotope of uranium. It's a particular isotope of uranium that has an atomic number of 232. It decays to this isotope of thorium, which decays to this isotope of radium, which decays to this isotope of radon, which decays to this particular isotope of polonium, which decays to this isotope of lead, which decays to other isotopes of lead, and then finally, we end up with this lead isotope here. So that's an example of a radioactive decay chain. It's a long radioactive decay chain involving many different decays. It involves both alpha decays that take you diagonally on this plot and also beta decays that take you vertically on this plot. And so many cases of radioactivity, we have decay chains, sequences of radioactive decays, rather than a single decay of a radioactive nucleus to a stable nucleus. On this slide, I just want to show you the equations that describe a radioactive decay chain that consists of a radioactive nucleus A decaying to a radioactive nucleus B, and then that radioactive nucleus B decaying to a stable nucleus C. So a chain that we could describe as A to B to C. That's a radioactive decay chain. This is the simplest radioactive decay chain. And we're going to look at the equations that describe this one, and they're quite complicated. Imagine if you had a more complicated radioactive decay chain, like the uranium chain, like the thorium chain, then you'd have even more, much more complicated equations. So the differential decay laws describing this decay chain, I've written upstairs here on the left-hand side of this slide. And then the integral version of the decay laws describing this decay chain, I've written downstairs here on the left-hand side of the slide. Let's start with the differential equations, and then we'll move on to the integral equations. So we now have three differential equations that describe the change in the number of radioactive atoms A, radioactive atoms B, and stable atoms C. So we have dNA dt, dNB dt, dNC dt for the change in these species. The radioactive law for species A says that its number is changing because it's decaying, because its atoms are decaying to species B, is changing by this amount over here on the right-hand side of the equation. It depends on its decay rate, and it depends on how many atoms there are of species A. And the minus sign is just saying that these atoms are disappearing. The change is negative. This is the law we met earlier on, when we just had a single radioactive decay. Now let's look at the rate of change of species B. So dNB dt. So this is more interesting. This has two terms over here on the right-hand side. But why are there two terms? The first term is the production of species B due to the decay of species A. So when A decays, it produces B. And so that there's a term that involves the number of species A and the rate at which they decay, and that increases the number of species B. That's the first term. And then there's a second term that corresponds to the decay, the radioactive decay of species B. So it's a term that involves the number of species B, NB, times multiplied by the decay rate of species B. And it's a negative term because it removes species B from the sample. So that's why there's two terms for species B in the middle of this decay chain. And then finally for species C, it's stable so that there's no removal of species C. There's no negative term. It's being produced though by the decay of species B. So the increase in the number of species C atoms is equal to the number of species B atoms times the rate at which they decay, and it is positive. So these are the three differential equations now describing the three populations of species A, B, and C due to the radioactive decay chain. Now we're interested in the integral version of these three differential radioactive decay laws. And so that's a matter of integrating these three coupled differential equations. They're coupled through the numbers of the atoms, NAs and NBs and NCs, and they're coupled through the decay rates, lambda A and lambda B. Now, the solutions, the integral forms I'm going to show you on this slide are for a particular initial condition of the decay chain, which would be a common initial condition. We're going to imagine that we start only with atoms A. There are 0 atoms B at time 0, and there are 0 atoms C at time 0. So that's our starting point. That's our initial conditions, kind of our boundary conditions. Based on those initial or boundary conditions, you can integrate the differential forms to get the integral forms, and you get these three equations for the time dependence of the number of atoms A, the time dependence of the number of atoms B, the time dependence of the number of atoms C. Over here on the right-hand side of these equations, you see a common factor. That's the number of atoms A that you started with. Everything scales with that. The more initial atoms A you have, the more populations of A and B and C you have as a function of time. The less number of atoms A that you start with, then the smaller the populations in A, B, and C as a function of time. And then you have that common term multiplied by these different forms of exponentials. Now, the exponential functions themselves, if you look at them, there's two distinct forms. There's e to the minus lambda at, and there's e to the minus lambda bt. And that's probably obvious that those are the only two time dependencies that these populations can be built out of, because there's only two decay rates, the decay rate of atom A, the decay rate of atom B. And so you only get two exponential decay curves, one that has a time dependence of atom A, one has the time dependence of the decay rate of atom B. If you actually want to derive these, the way to derive these is the most straightforward, the most simple way to derive these three equations is to say, look, there's only two time dependencies that the populations of the atoms can have. The populations of the atoms must have a time dependence that corresponds to some superposition of e to the minus lambda at and e to the minus lambda bt. So all these populations can be built out of those time dependencies. Those time dependencies can be multiplied by some coefficients. And there'd be different coefficients for the population of atom A, the population of atoms B, the populations of atom C. Using the boundary conditions, you can figure out what those coefficients are. And so that's how these equations were solved. You see that they're quite complex equations. And they're quite hard to read or to visualize or imagine exactly what the time dependence looks like. And you can imagine, I'm sure, that if you had a sequence like the uranium radioactive decay or the thorium radioactive decay, so those chains involve many different isotopes, many different unstable radioactive isotopes. You wouldn't just have three differential equations for the decay law and three integral equations for the exponential decay curves. You'd have many differential and integral equations, and it would be a very, very complicated problem to solve them. What we're going to see is that by applying Monte Carlo methods to radioactive decay chains, it is easy for us to compute the time distribution of all the different atoms in a radioactive decay chain. For this chain involving two radioactive atoms, it's quite a bit of work to analytically calculate these expressions, but it's very straightforward to use the Monte Carlo method to determine these populations of the different species as a function of time. And for more complicated chains, it would be extraordinarily time-consuming to calculate the populations of the different atoms analytically. But it's very simple, very straightforward to calculate the populations by the Monte Carlo method. And so we're going to explore that Monte Carlo method as a very convenient way, as a very straightforward way, a very reliable way of solving this problem.